And we also wanted to know the torque. Okay, so the torque is simply comes from the converted power, which is EAIA, and also equals to induced torque times omega m, right? So the induced torque is simply EAIA divided by omega m. Okay, so it will be 236.2 times 253 ampere, okay, divided by 1586 times 2 pi over 60. We have to convert this to radian per second, right? Okay, so this will give you the induced torque of 36 Newton meter. Okay, and we also wanted to know the power, right? So the power output, the output power is actually depends on how much rotational losses that we have. Okay, so if we have no rotational losses, okay, in this case it didn't say anything about rotational losses, but if we don't have any rotational losses, so the converted would be equals to the output power lah. Okay, so it would be EA times IA lah, if we have P rotational equals to 0. Okay, alright, so if IA is 50.7 ampere, then obviously we will repeat the whole calculation again lah. So we know that the induced voltage, when the input current changes, we will have a different EA lah, right? Because right now the voltage drop is much larger, kan? Because there's the armature current is larger, so obviously the term IA, RA plus RS is larger. Okay, so here VT minus IA, RA plus RS, this part has a larger term. Okay, so 240 volts, sorry, minus 50.7 times 0.09 plus 0.06, and this will give you 232.4 volts. And we can see that in comparison with the first one, we have 236.2 volts, right? So the induced voltage has now reduced. So we will expect that it also affect the amount of speed as well as the output power lah. Okay, alright, so the magnetomotive force, okay, that we have at this point is 33 turns. Obviously it's Ni, right? NIE. So times 50.7 ampere, so it will give you 1672 ampere turns. And if we take a look at the table, 1672 is between 1500 and 2000. So obviously we will need to compute a new M lah, because the linear interpolation now becomes between the third and fourth point. So between the third and fourth point, we assume this is linear. Okay, so that's why we need to compute a new M lah. And the new M is y2 minus y1 over x2 minus x1, which is in this case between 2000 and 1500 and 212 and 188. So again 2000 and 1500 divided by 212, 188. Okay, so 212, 188. So 100 divided by 2. So it will be 20.83. See, it's different slope. and then we will have to find a different C as well. Okay, so I just simply say I put 2020.83 and 212 plus C. So C is 2 is minus 2416.6. Okay, so the equation now becomes y equals to 20.83x minus 2416.6. Okay, all right. So if you want a full equation for linear interpolation, if we rearrange this equation, we will also get you can Google this. Is basically this equation is everywhere. So linear interpolation, if we want to know the amount of value that we have, the formula to obtain an unknown point, okay, between an interval is basically y equals to y naught times x1 minus x plus y1 x minus x naught divided by x1 minus x naught. Okay, so this equation will work for if we know the interpolation between interval of x naught and x1. Okay, and then the unknown is basically x and y. Okay, so in this example, for example, you know that the range that you have is for x is 188 and 212, right? So the y naught and y1 is simply 2000 and 1500. Oops, sorry. 1500 and 2000. Okay, so you can also plug in this equation. We want to know the y and x. So y here means the f and the EA. Okay, so f we usually calculate it first, right? So we already know the y, but we don't know the x yet. Okay, so from the equation we can put something like this: y equals to y naught is 1500, and then x1 is 212, okay, minus x plus y1 is 2000, okay, 2000, and then x is we don't know yet, minus x naught is 188 divided by x1 minus x naught, which is 212 minus 188. Okay, so from this equation, y is already calculated because we know this is f, right? So f we already calculated as 1672. So we know 1672 times 212 minus 188 equals to 1500. 212 minus x plus 2000 x minus 188. So from here we can also get x. Okay, so we can use this general equation, or you can use the way to find the slope first, and it's the same thing. You can get the same value, plus minus some significant figures lah, depending on how you calculate as you go along. Okay, so then you repeat the same calculation for the rest. Okay, once you get an EA coming from here, okay, so x here is EA lah. Okay, so EA for this second value, okay, for IA equals to 50.7, the EA that we get is 1062, 197 volts. Okay, so this we have at n equals to 900 rpm lah. Okay, because the table we get at 900 rpm. Okay, so the speed of the motor at the condition of the calculated ones, which is 232.4, is simply we do the same equation again. Okay, so EA from the 50.7 ampere, right, and the speed at 50.7 ampere. We compare with EA that we have from 900 rpm, and then the speed that we have at 900 rpm. Okay, so it's 197 volts over 900 rpm, and then the EA is 232.4. So 232.4 volts divided by, this is the speed that we want to know, right? Okay, so this speed is 1062 rpm. Okay, so the power converted, obviously, if we don't have rotational losses, sorry, not power converted, the output power is actually P converted minus all the losses lah. Okay, so rotational losses and everything. So if we ignore that, it will be P out equals to P converted, which is equals to EA times IA. Okay, so or tau induced torque times omega, anything, since we don't know induced torque yet, so basically we can calculate from here. So EA is 232.4 volts times IA is 50.7 ampere. We will have 11,780 watts. Okay, so the induced torque is, therefore we use the equation of P converted here, EA IA over omega. So it's 11780 watt divided by so the speed is 1062 rpm, so we will have to times 2 pi over 60 to get radian per second. So eventually we get 106 Newton meter. So you can repeat as well as for IA is 76 ampere, right? Or this is 100% rated current, or and IA equals to what is the last one, 101.3 ampere, which is at 133%. So it's the same calculation, and we will see that the induced torque eventually will increase, and the power converted or output power is also increased, and the speed will get lower and lower. Okay, this is actually consistent with the theoretical part of this DC machines, because obviously if we have more torque produced, we will have a slower speed of the motor lah, because we will have to compensate for the increasing torque demand from the application. Okay.